Okay, so flatness is what the initial part of my 6 lectures. I think I'll be talking about flatness, faithful flatness, and the flat descent for at least 2 lectures. So let me see how much I can cover, and I will be, I think I will be more or less self-contained. And as Professor Patil has already said that this course definitely requires some kind of familiarity with the basic commutative algebra course to the extent of at least first 7 chapters of Atia MacDonald. So we are assuming that, but again, certain main topics, some main theorems, main concepts, we will definitely run through. Okay, so I'm starting with the tensor product. I'm sure all of you know that if I have R modules, then tensor product is defined as this R module T, Mn and R modules T, and with an R bilinear map from, yeah, so I'm calling this as the tensor product, such that it satisfies this universal property. That is, if you have any R bilinear map from M cross N to another R module E, then, and this is your tensor product is this R module together with this bilinear map, right? Such that this factors, that means you get a unique R linear map from T to E such that this diagram is commutative, okay? Such that this diagram is commutative. So this is, and then you can actually, by the way, let me explain that whenever you see this E stroke T, this means exercise stroke tutorial. So that means there are certain things which we are not discussing in detail. It will be discussed. It is to be taken as an exercise. It is to be discussed during the tutorial. Okay, and you will find many such in these lecture notes. And these lecture notes will be shared immediately after the lecture is over. I will just scan it, make a PDF out of it, and then share. And a more formal version in LaTeX, etc., will be shared also soon. Okay, so tensor products are uniquely determined by the defining universal property up to canonical isomorphism. Well, if you have studied, you must have done this. This is kind of a very standard procedure that you assume that there are 2 R modules and 2 bilinear maps, tau and tau dash, and then which satisfy this universal property. So what you do is you just apply the universal property twice, and then you will be getting for this tau dash, you will be getting this direction, this R linear map tau dash tilde, and this tau tilde will be the one when you are applying the bilinear universal property for this map, for this bilinear map, and for this as the tensor product, right? And then you can check that their composition, etc., will be identity, and then uniqueness assumption on the map. Uniqueness, so this is unique. This is unique. So uniqueness assumption on the map actually shows that these are actually isomorphisms, and therefore T is isomorphic to T.
Hello?
I have not explained it in further detail. Yes, please.
Sir, can you put the note at the center, please? Because the left side is not. Yeah.
Better?
Yeah. Shift.
Let me try. Now, actually,
now it is okay.
The same essentially. Is it better now?
Yeah, sir. Yeah.
Okay. So, and then this is a very standard notation. I am sure you have seen this, that tau of x comma y is x tensor y, right? So these are the elements in your tensor product, and it is usually the tensor product, this T. Once you have established that it is unique up to a canonical isomorphism, so you might as well say that this is in M tensor N over R. Okay, so this is going to be our symbol for the tensor product. Okay, and again, this is something which is understood, but it's better to spell it out once, that bilinearity of this map tau actually says this, that whenever you have this kind of tensors, and then you have the linearity here, linearity in this argument, then because of bilinearity, you take the A out, then take the B out, take the additivity gets distributed over the tensor product, etc., and you get such an expression. Okay, so this is tensor product, and then the tensor product T exists for arbitrary R modules M and N. You know, this is often a very interesting fact that people say that it is enough to have just the universal property. there are comments that you understand the universal property and then this you should learn, but then you can forget it. But let us see whether we can actually ignore or forget it, or we should be knowing and we would have a use of this. So how do we show that? So you can understand this is a construction, a universal construction in the category of R modules, right? So you would definitely like to know whether it actually exists. So the proof, if you have studied tensor product, you know, let me still go through it quickly once. So this is the way you prove it. So what you do is, this is what is called the free R module on M cross N. So what I mean by this is that, so this symbol for us should mean R raised to this bracket M cross N. You can take it to be the, so loosely speaking, it is so many copies, but you know, you need to be a little formal. You can say that these are all the maps from M cross N to R which are finitely supported. So that means at almost all places it is 0, fine. And then you look at these spatial maps, which are from, which you can say that this is from M cross N to R. That is, so this map is, so if A is in M and B is in N, then for a fixed choice of X comma Y, you can define this map as, if this X comma Y is AB, then it is 1 and 0 otherwise. So you can understand it is like those canonical vectors. Yeah, these are like those canonical basis vectors, right? So this is a good way of saying that this is in fact your canonical basis for this free module, this R raised to this bracket M cross N. Okay, now take this free R module and quotient it by this submodule, which is generated by relation. So you can understand now please see what I have said, that note that elements of R raised to M cross N as functions from this to this. I'm sorry, I should have said finitely supported, are finitely supported. Not all functions. So finitely supported functions from M cross N to R, and then X comma Y is being identified with the function, this E suffix X comma Y. Okay. So if this is a kind of an abuse of a notation, you can say. So really speaking, by this, I mean E under and then suffix X plus X dash comma Y. Okay. So what you are trying to do is that you are kind of killing the bilinearities. Okay. So you take the submodule Q generated by all these kind of elements and take the quotient. Now you claim that this R module T is actually your tensor product, in the sense that it actually satisfies the universal property which we have said. So what is that? That means if you take, I would have preferred to write it here. Anyway, I missed it. So if you take M cross N and if you take any R module E, then, and if you take any bilinear map phi from M cross N to E, then what you want is that from this is your T, okay? From here to here, you should be able to, this should give this bilinear map, and this bilinear map, okay, should give a unique linear map from here to here. Now, this is again, I am not very much keen on spending time on that, because see, I have mentioned E stroke T. So my suggestion would be, why don't you try it yourself? That, please give me a minute, please. I need to. Okay, so you can check it. This is very simple, that first you try to define this bilinear map from here to here. I'm sorry, what is that? This M cross N to this, let us call this as the T. Let us call this as the T. So you first define this bilinear map, and then what you show is that from here to here, you want to define a linear map using phi. So first you define here, and then you check that whatever your this map is, this is the canonical surjection, you can understand. And if you want to have a map from here to here, all you need to check is that your Q is contained in the kernel of this phi hat. Okay, so then this happens. So this is simple, and you should verify it yourself. If you still have a problem, you can run a discussion during the tutorials. Okay, so now this is an interesting question, quite a debatable one, that can you give an example of a situation where you need this explicit construction of tensor products? So I will be able to give you one, but also I will be able to show eventually that you can even avoid that. So if somebody has a good answer, that also we can take up and show that is there some result where you definitely need the construction and without that you cannot do. Okay. We will come to these situations eventually. Okay. Now, this is a proposition which says if M and N are R modules, then every element can be written as this finite sum of these. Sometimes they're called basic tensors. So this xi tensor yi for a finitely many of them, where xi is in M and yi is in N. Now, how do you prove this? So let me quickly just run through. Again, you can see I have this symbol here. So that means there are some parts which I have not, which I have kept which I have not discussed really. So let T be the submodule generated by X tensor Y, where X belongs to M and Y belongs to N. So what do you want to show basically? You want to show that if you take the submodule generated by these basic tensors, then you want to show that, so that submodule you have here, and you want to, if you can show that it is bijective, okay, this natural inclusion is bijective, then you are done. But the point is, how do you show that? So, well, that's a very simple way to show. Let me just quickly summarize it. That why don't you show that this T, what is that T? T is the submodule generated by these X tensor Ys. Why don't you show that this satisfies the universal property of the tensor product? Okay, then you will be able to show that this naturally is an isomorphism. Okay, and therefore you have proved your result. So, and doing that is kind of not difficult. So I have not explicitly written it here, but you can actually, I mean, I have, if you still have any difficulty, please do let me know, or the tutor know. Okay. Okay. Now, quick listing down of some properties. This again, I have kept as E stroke T because these are supposed to be the basics. So, but we will be more than happy to discuss if necessary. So, if you have, so this is the notation. So, suppose I have some pre-assigned elements called Z suffix X comma Y for X in M and R Y in N, and they are elements of some R module E. Now, if you have a map from the R linear map from the tensor product given by this assignment, that this X tensor Y is going to these pre-assigned elements Z, X, Y, then this map is unique. And then suppose that this, you have a map psi from M cross N to E given by this pre-assigned elements. These are the pre-assigned elements in E, such that the map is psi is bilinear. Then there exists an R linear map psi tilde from this to this. You know, this is the property of the tensor product, such that psi tilde of this is ZXY for all X in M and Y, and psi tilde is unique, right? So anyway, your the moment you are defining a map using the universal property, the moment you have a bilinear map out here, and then it induces a unique linear map. So that part is always there, okay? Okay, and these are some, I mean, I thought, by the way, what I am following for this part is primarily the book by Siegfried Bosch. Okay, so mostly, I mean, later on I will slightly differ. I'll let you know what that is. Okay, so the notations and everything are pretty standard. Should not be finding it difficult to understand. These are certain very basic properties that if you tensor, if you have a free R module, and suppose it's a rank 1 R module, and if you tensor with that, you just, it keeps the module unchanged. Flipping the positions of two R modules in the tensor product does not make it change. And this you can push this bracket over here, kind of, kind of an associativity. Okay. Now, see, this point is, okay, so let me first speak and then let me just say the crux of the matter. And if you have a family of R modules and N is another R module, then there is a canonical isomorphism. So every time I am using the word canonical isomorphism, I need to explain that. And lastly, M is a free R module with the basis xi, I is the index set. Then for any R module M, you have an isomorphism from here to here. Okay, so because M is a free R module, so that means you have, this is like direct sum Rxi, I in I. So what you are saying is that you can take the direct sum out and then you just get this. And this, these are Rxi is isomorphic to R. So each one is isomorphic to N by this. And therefore, you have this n raised to bracket I. So it is a similar notation to what we have said just now. So you know, it's something like that. I just now defined that r raised to m cross n within brackets, so you know, something similar. Okay. What I need to say is that whenever you see this, what I intend to say is that use the universal property. So use the map induced by the universal property. This is one thing. Another is, if I'm sure you are already comfortable with that, but still sometimes people do make mistake. I mean, it is never ever try to create a map from the tensor product. What you do is always use the universal property. You just create a bilinear map from f cross m to m, and tensor product takes care of the rest, that it automatically induces a linear map from f tensor m to m. Okay. Now you need to check that it is in fact an isomorphism, right? So how do you do it? Well, a piece of advice, usually what happens is that, of course, you can check the kernel and image, but sometimes what happens is that giving a map in the other direction, which is the inverse of the map, is often easier. Okay, so these are certain things, if you keep on mind, then proving these things are sort of routine. There's not much difficulty. Again, please understand this as an exercise come tutorial. So please make sure that you understand this well, you work it out. If there is a difficulty, get back, because otherwise it will be impossible to know whether you are facing any difficulty at all. Okay, so I think, yeah, okay, one more page on tensor product, and then gradually we will move on to flatness. Okay, so a caveat, that means a word of caution. What is that? So first of all, this is a very standard example. I'm pretty sure you have seen this, that if you look at these two tensor products over Z, then, and if you look at this element, now this element here and this element seen here, they definitely are not the same in the sense, because see here, because of the bilinearity, you can take the 2 out and push it over here and it becomes 0. Okay. So on the other hand, this is not the case. Here, this is a non-zero element. Fine. So this is one thing. And you will see that this very fact actually also will show that when we come to the topic of flatness, you will see that this very example actually gives us the motivation of defining flatness and all. Okay. This is one thing. This is also a very important thing. So if you look at the previous page, maybe, yeah, I should have said that. If you look at the previous page, so we have done what? So we have here, it is about as defining a map, right? So how do you define a map from the tensor product? That's the main thing. So all you need to do is, if you have some elements in mind, then you need to define a bilinear map from here to here, and then tensor product automatically defines the unique linear map, right? Then if you come here, then what it is showing is that the behavior of the tensor product in terms of associativity and all. Here you are discussing the behavior of the tensor product in terms of, I mean, how does it behave with the direct sum, right? And especially with the free modules. But there's no mention of the Cartesian product as such, whatever that means. So I'm exactly this in this caveat, I'm trying to say that. So what I'm saying is this compatibility of tensor products with Cartesian products. Now let me read it out, because this I would like to add as a problem. And in fact, the answer is here, but the verification is required. So if you have a family of R modules and N is another R module, okay, then it can be proved that there is a canonical morphism of R modules from this. So this is the Cartesian product, tensor product with N, to the Cartesian product of Mi tensor N. Okay, now how do you prove this? This is the first part. Once again, appeal to the universal property. And this is an isomorphism if I is finite. So that requires verification. Okay, but lambda need not be injective or surjective if I is infinite. So please keep this in mind. So when we were discussing the commuting of the tensor product with the direct sum, and in fact, we will see it further, it will be used, then your this assumption was not necessary. You just took any free module, for example, on arbitrary index set, right? I mean, basis indexed over arbitrary set. But here, when you are talking about just the tensor product, then if you want to talk about how the tensor product behaves, you do get a map, you do get an isomorphism also, provided you are taking the product over finite sets. And I have given you a few important examples, and another one, that you can have a situation where you have non-zero modules giving rise to the zero tensor product. Okay, and in fact, that example will come from here, if you know. So this is a possibility. In fact, when we discuss the faithful flatness, you will see that this again would come back as an issue. And these are two examples which I'm not telling you right now why I have written these, but you can understand that they possibly have got something to do with these comments. Okay, so these will be discussed in the tutorial. And in fact, it will be added in the next tutorial sheet, not here, not now, the one which is being shared today. So it will be added in the next tutorial sheet. So any questions so far?
Hello.
No? Okay. Good. Okay, so we are now in a position to define the flat modules. Yes, please.
Yes, sir. There, in that example you're giving, where the element was non-zero in one and zero in the other, like tensor one. Why is it non-zero in the product of 2z tensor z by 2z?
The previous page?
Yes, that example which you're showing.
Here?
Why is it non-zero 2 tensor 1 bar in 2z? Like, how can we know that it's non-zero?
Oh, are you asking why is it non-zero here?
Yes, sir.
So 2 can't go that side, right? The ring is 2z.
But well, I believe I have to give you answer through a map, perhaps. No, see, the point is, why is it 0 here? That is clear, because I can push 2 on this side and it becomes a 1 tensor 2 bar and it is 0. But you are asking, how do I show that this is non-zero here, right?
So probably we can define a bilinear.
One way is 2z is isomorphic. I mean, as a z module is going to be isomorphic as z, right? And then you have z2 through the canonical map. Okay. So if that happens to be 0 there, then your image will also be 0 there. Do you understand what I mean to say? So if you have the isomorphism on this left place, okay, and then you have the isomorphism, and then if you tensor, then you will see that actually it requires a little more discussion. So please allow me to give your answer a little later, okay? No, it does require a verification, because often a tensor is not 0 somewhere. You cannot say by brute force. It is 0 here is clear. I'll give you an answer in a minute. Please wait. Okay.
Sir.
Yes, please.
Sir, M is R module, then M tensor R mod I is isomorphic to M mod IM.
Right, absolutely. That's exactly what I was coming to. I'll come to that. Yeah. So because that will be stated a little later. Yeah. So what Joydeep is saying is basically this is M and tensor R mod I. So this is M mod IN. Okay. And from that, it would follow that you cannot, if it is 0, you will have a 0 there, and that will create a contradiction. Yeah. May I just move on? Okay.
No, you can pull the 2 out of the first factor and then push it to the second factor to make it 0.
No, that is the answer to the fact that why it is 0 in the second module. But the question was, why is it non-zero in the first module?
Sir, can I say something?
The question was, why is this element non-zero in the first module? The question was not, why is it 0 in the second module? That is clear. That is because 2 can be pulled out and pushed in here. But why is it non-zero in the first module is the question which needs to be sorted out. So that is what yes. Please answer whatever you want.
Sir, if I take the submodule generated by 2 tensor 1 and take the quotient, then I think it will be isomorphic to Z mod 2Z. So,
why? Why is that so?
Because, sir, in the first place, I am getting 4Z. And
but how do you know that you can just push the first factor here and the second factor there? Well, essentially what you are saying, it makes a lot of sense because there's exactly what Joydeep said just now. See,
yes.
Let me show you. This is what is true. If you have M tensor R mod I is isomorphic to M tensor IM. Okay, if the tensor is fine. So what
Yes.
having here is that it will be something like 2Z quotiented by 2Z, 2Z. Okay.
Yes.
This is your I. This is your I and this is your M. Fine. That's exactly what you were saying. I know. Now the question is, if you have this element is 0 here, then it will be 0 there because of the isomorphism.
Right, right.
And this is where it will contradict.
Yes, yes. Huh.
Yeah, precisely. Absolutely correct. So that is exactly. So I said I would like to wait because I have not yet stated those properties yet. So that would take care of it. Okay.
Sir?
Yes.
Sir, when we want to say some element is 0 or not, we can produce a bilinear map, which is not vanishes at that tensor. So that will take care of it. Say here 2Z tensor with Z mod 2Z, we can produce a bilinear map from 2Z cross Z mod 2Z to 2Z. Say 2 tensor 1, you can send it to 2.
No, 2 tensor 1, you cannot send it to 2.
Sir, is it at all well defined?
No. See, the point is not that. I mean, point is that, see, so let me show you.
Sir, we can define just a bilinear map from 2Z cross Z mod 2Z to Z mod 2Z.
Yeah. Okay. What is the map?
The image of 2, 1 is non-zero. That is enough.
Cross Z mod 2Z to Z mod 2Z. Yeah. What map would you take?
So just take, say, any element 2n, m bar. Send it to n times m bar.
N times m bar.
Yeah. So 2n, m bar. Send it to n times m whole bar. Yeah.
And you just make 2 disappear.
Yeah.
Okay. Now?
That is essentially the same map sir was telling, right? Through the isomorphism.
Yeah, but we can always give a bilinear map from 2Z cross Z mod 2Z to something. But
you are correct. You are correct. See, let us wrap up this discussion. See, the point is, you can either you discuss it at this level. This is the bilinear map, and this is so. This automatically you have this bilinear map here. Okay. So this is the tensor product, and you have this bilinear map, which I call tau. Now, question is, instead of this, if you take this 2Z, 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 essentially you are working here because otherwise you won't be able to show the non-zero-ness. You are not able to decide it over here. So you would like to take it to an R module where you would see it as a quotient and decide the linear. So basically, if it has to be 0 here, it will be 0 here. But 0 here would mean that it should be here. But you cannot write it as kind of, a 4x kind of an element. So using the bilinearity or using this linearity as an isomorphism amount to the same thing. That's exactly what the idea is. See, here you are not able to push the 2 out of the picture is the main thing. Okay. So it comes into the quotient and 2 remains as it is. You won't be able to push 2 out of this situation. On the other hand, that is not the case here. Here you will be able to push 2 out, and therefore once you have this, you will have Z mod 2Z, right? So once you have this Z mod 2Z, then anything here, it will eventually collapse and come to 2Z because, see, what you are saying in terms of bilinearity is you are pushing that 2 on the right-hand side. What you are saying in terms of linearity is also same thing, that you are pushing that 2 so that it comes to the denominator. Okay. So just wait a little because these things will be discussed again because this 0 is a big issue in tensor product. And in fact, you know, there is a very famous statement which often is discussed and debated, that whether the proof is complete. So once I come there, you will understand it even better. So let me go to flat modules now, and then I'll come back to your questions and convince you. Okay, so if you have two R modules, MM dash and another two NN dash, and if you have R module homomorphisms, then this gives rise to this R module homomorphism. So this is the tensor product of the module morphisms, the module homomorphisms. And this is a kind of a standard application of the universal property, right? Because what you would be doing is, again, you remember, never ever try to give the map from here to here. Rather, you give the bilinear map from M cross N to this, and then universal property takes care of the rest. It induces a linear map from M tensor N to M dash tensor N dash. Okay, so this is that map, and this is the symbol. Fine. And in particular, if you have N is equal to N dash, then you can take your psi to be the identity map. And then this map is phi tensor identity N, that is going from M tensor N to M dash tensor N. So this part, I'm sure it's clear to you that why this map exists, that is by the universal property. Okay. Now, this is also a very standard property of the tensor product, namely the right exactness. This is how it is called. That if you have this exact sequence of R modules, this M dash M, M double dash to 0. So when you say it is an exact sequence, let us quickly recall, that means you have this R module maps, and then you have the image of this is equal to kernel of this. And similarly, the image of this is equal to kernel of this. That means psi is surjective, right? So at every spot, it is exact. That is the definition of an exact sequence. Then if you take any R module M and N, and if you tensor, then obviously here we have just now discussed. So automatically you have the tensor product of the maps, and then it gives rise to another sequence, right? So question is whether that is exact or not. The answer is yes. Okay. So once again, now whenever you are checking the exactness, which it means that you have to check what? In order to check that this is exact, you have to check that at each spot it is exact. So that means image of this is equal to kernel of this. And again, this map is surjective. So this is the summary, that image of this is contained in kernel of this. That is true. Why is that true? Because you already have that this is an exact sequence. So therefore, definitely psi composition phi is 0, right? And therefore, if you tensor it with this N, and then if you take the identity, then you will be able to see that if you take an element here in the image of this, then you apply here, then you kind of nicely distribute your psi over phi, and then it kind of reduces it to 0. Okay. Now look at this. Now this is very important. Okay, so here you have this, and you have just the the identity map. So this induces this map psi bar. So can anyone tell me what exactly do I mean by saying this? That this induces this map. Look at this. This is the quotient. Fine. So now, when do you say that this induces the quotient?
When the denominator is contained in kernel.
Done. Just done. So this is the universal property of the quotient, right? So since this is true, therefore it induces this map psi bar. So now, in order to show that this is exact, what we are left with are these two facts. So if we can show that, so if you want to show that, we want to show that image of this is equal to kernel of this. Now that will be if and only if psi bar is injective. And then I have to show that the psi tensor identity map is surjective, which is equivalent to show that psi bar is surjective. Okay, so it's just once again, you can see this symbol, because these are small checkings which you just need to do this checking, and then immediately it can be sorted out. That so basically what you have to show is that psi bar is an isomorphism, right? From this quotient module to this module. Okay, now what did I say just now? I said that in order to show something is an isomorphism, sometimes it is wise if you try to give a map in the other direction. So that means you are trying to give a map from here to here, which I call psi. And what is the other thing that I said? I said never ever try to give map from the tensor product. Give it from the Cartesian product, a bilinear map, and tensor product universal property takes care of the rest. So you basically have to give a bilinear map from M double dash take cross N to this. Okay, and then bilinearity and tensor product will say that there is a map, and then you need to check that the compositions are identity. Okay. Okay, so yeah, so now this is, yes, right. This is, I wanted to mention this, that we will discuss another proof using the contravariant functor home in the tutorial. So this is one thing. Another is just what I said, no, that that the property of tensor product, how does it behave with the infinite Cartesian product? And this one, so you can give another very nice proof of this fact, okay, using this, that, by the way, this is basically the universal property. Do remember this. This is very, very useful. And in fact, this I will write in detail and share it with you in the tutorial sheet. That, so the bilinear map from M cross N to E gives rise to a unique linear map from M to, so it's a linear map from where to where? It gives rise to a linear map from the tensor product to E, right? Yeah, so yeah, anyway, I don't want to, I mean, anyway, what I mean to say is that, see, if you have a bilinear map, so that automatically it gives rise to a linear map from M to homeny, in the sense how you just fix one element in that N, and then kind of it gives rise to a map from M to homeny, in the sense that you take that, suppose you have the bilinear map from M cross N to E, that it automatically, if you fix for each X in N, then you can define a phi X, isn't it so? And that will be a linear map. Linear map from where to where? So it, for each X, you get a linear map from M to NE. Okay. So because it is individually linear with respect to both the arguments. So this is exploited. And then if you use home, then you can give a very nice different proof, and that is quite useful. So I don't want to discuss it today, but it will be added in the tutorial. Okay. Okay, now some immediate corollaries, that if you have a submodule of an R module M and N is another module, then this can be seen as a quotient module of M tensor N. How basically, let me just quickly pass through these pages, that, you know, this is the kind of the standard exact sequence where M dash is a submodule, and therefore you have the inclusion, and this is the canonical surjection. This is an exact sequence. If you tensor it with N, you know it is right exact, and therefore image of this is equal to kernel of this, and therefore M tensor N over the kernel, that means image is isomorphic. So this is fine. So therefore you can at the most say this, that if you have a quotient like this here, and then this tensoring with N, you can say that this is indeed a quotient of M tensor N. Okay, but you definitely cannot say that this is sitting inside this. That is the major problem, and that is the reason why you come to the notion of faithful flatness and faithful flatness eventually. Okay, another corollary, this is very important. This is exactly what kind of Joydeep was trying to use and said, that so if you have an R module and A is an ideal, then there's a commutative diagram with exact rows. So it says a little more than, so basically what you want to show is that this is an isomorphism. So if you have R module N and if you have an ideal A, then R mod A tensor N is isomorphic to N mod AN. So you want to show that this is an isomorphism. So basically it's this kind of a diagram chasing. What you do is you just take this. So you know, what is this coming out from? So you take A contained in R, going to R mod A, going to 0. So this is an exact sequence, tensoring with R, left exactness is intact. So you have this exact sequence out here. And then this is also the standard inclusion here and the standard surjection here. So and here, in fact, you know, this is the kernel is AN and the image is AN and this is injective. So you have a nice short exact sequence here, right? So now if you just follow these maps, that how this tau dash is surjective, and tau is the canonical isomorphism, because we have actually proved this, or rather mentioned this. And then you can show that this has to be injective and surjective both, basically. Okay. So this kind of diagram chasing settles the matter, that so if you take this, then it induces the top row with tensored by N. And one has to note that the image of this, so basically you push it over here, then come by this, then the image of this is exactly equal to AN, because this is just a standard inclusion, okay? So AN as a submodule of N, and then you can show that this is exactly this. So, you know, these things are better done than like I explained to you, because if you just sit with a pen and paper and just follow the diagram chasing, you will get it. It's not difficult. Okay, but what is interesting, let me come to that stage. Yeah, so once again, that comment that you do have an inclusion here. And if you take this tensor product with respect to Z2, then you have an injection here, you do not have an injection here. In fact, what you get over here just now, you have seen that the moment you have elements here, when they go there, then you can actually make them zero, right? So you have a zero map here, right? So therefore, injectivity is not restored. That's exactly what you have discussed. Okay, so now it naturally gives us the definition, enough motivation, and now the definition that you say that an R module is an R module N is flat if you have any map phi from M dash to N, and then if you tensor, then if this map is injective, then this map is injective. So the left exactness is, if the left exactness is also true, then you call it a flat module. And the ring homomorphism, suppose you have a ring R and R dash, commutative ring with identity. Well, I forgot to mention that rings are all commutative with identity, but this is understood because it is a commutative algebra course. So,
just a minute, sir.
Just a minute, please. Let me just quickly finish this and then I will take your question. So if you have a ring homomorphism here, so you know, then R dash has a natural, in fact, an R algebra structure, right? I mean, it has a natural R module structure, and you call this ring homomorphism is flat if R dash as an R module, that is through this as a structure map, if R dash as an R module is flat. Yes, please. What is your question?
In that remark, second line, that Z, the 2 is a tensor with Z mod 2. The tensor is over 2, is it right? Is that what you are saying?
The tensor is over Z. The tensor is by Z2. Yeah. Tensor is over Z. The ring is Z. So that makes you, you know, the ring is Z. So that makes you kind of push this by, use this bilinearity, you know, take this out and push it over here.
Yes, sir. But the 2 is a tensor over Z, itself is 0, right?
What over Z is 0? You mean this? No, this is not 0. Just now that was the discussion, no?
No, that was over 2Z, right? The tensor is over, you had taken the tensor over 2Z.
Always. No, not over 2Z. If over 2Z, you don't have a module structure for this, the other one, no? So it is over Z. See, the tensor is over Z. Both are Z modules. Okay.
Yes.
The tensoring is over Z. But in this case, you have seen that this is highly this here you have non-zero elements, right? And then when you push it over here through the standard inclusion and then by the tensoring, that dwindles to 0.
So I'm sorry, why there we have a non-zero element in the domain?
2 tensor 1. That's
but
exactly.
You can over Z you can take the 2.
Over Z you can take the 2 out of what?
2 tensor 1. Because the tensor product, the base ring is Z, not 2 is it?
No, sorry, I don't think I understand. Let us go back to that.
So if you take out 2, then what will remain in the first component?
Exactly. You mean here, right? The tensoring is always over Z. Now, what?
Okay.
I mean, here the elements are of the form 2x, correct? Okay.
Yes. I'm sorry, sir. It's my mistake. I'm sorry.
Understood.
I'm sorry. It's a blunder. Sorry.
No, not a blunder. It's all right. Okay, good. Yeah, I mean, too many things going too fast. So probably. Yeah. Anyway, so, but this. If you spend a little time, you will immediately see. It's not a very big deal. Okay. So now we are coming to proposition. We will be having this kind of diagram chasing, okay? But actually, you know, I mean, always asking this question of whether it is 0 in the tensor product or not. Sometimes people are casual, but it is not a question to be a very casual about, because tensor products do become zero when the actual modules are non-zero, right? And there are elements which are therefore after you tensor them, they can become zero. So it is really an issue, and that kind of forces us to define these notions, etc. Okay.
So is there any formula for that? When tensor is zero, then what happens to the components? Is there any particular formula?
No, not really formula, but we will come to some certain characterizations. Yes, we will come to that. Yeah. Not a formula really, but you will see. Please wait for a couple of minutes. Okay, so now here this is also this is a very nice and important characterization of flatness. So if you have flat, so remember please, what is the definition of flatness? That once you tensor by that module, it retains the injectivity of the map. That's all. Okay. Okay. So now you have the following statements are equivalent. First is n is flat. Then if you have a short exact sequence of R modules, then this sequence is exact, which it's kind of understood because your right exactness was always there. The left exactness was an issue, but flatness ensures that. Then you have the other one, that is, if you have an exact sequence of R modules, then this sequence is exact. So this is just a, how do you show that what is the exactness? That means at this spot, the image of this is equal to kernel of this. After you tensor it out, then you have still the image of this equal to kernel of this. Now the first part is, for 1 to 2 is okay. 2 to 3 also, it's not a problem really. So what you do is basically, if you please go through my this write out after I share it with you, you will immediately understand. So every time, so you have this m dash. Sorry, I should have mentioned it here. So here I mean, yeah. So I have mentioned it here. So I mean to say that here I have my phi, here I have my psi. Okay. Yeah. So once you have this, then you have your m dash and then to image of phi, right? So you have this map. That is clear. This map is phi, clearly. And you have your m, your kernel of phi, psi, that is, this kernel of psi is contained in m, right? And then going to image of psi. Okay. So since you have the, once you have this exact rows, and then what you do is here you have your original exact sequence. We are proving 3, by the way. Okay. So I have started, I should mention here also. So I have a exact sequence here. This is my original one. And basically, again, I'm doing a diagram chasing. I want to show that this is exact after I tensor by n, right? Now, what I'm doing is here, I'm every time for this map, I am having this image phi. And for this map, I have having this kernel psi. Okay. So look at this portion. And again, you have this here. And then again, for m double dash, you have the image of psi, which is here. And you have this portion. So you have the exact rows here. Now, since the first and the third rows, and by the way, what is 2? What is given to you? That whenever you have a short exact sequence of R modules, then this sequence is exact after you tensor by n. So basically, therefore, you are trying to create a short exact sequence of R modules out of this, isn't it so? Okay, so since the first and the third rows, they can be completed to form a short exact sequence, okay? Now, from 2, it follows that when you tensor them out by n, then you still have a short exact sequence. Now, can somebody tell me what I mean by saying that they can be completed to form short exact sequence, the first and the third row? Then I'm going to the next page. It will be clear, but can you see this from here? Please, I read it out again. Since the first and the third rows can be completed to form short exact sequences. What does that mean? And how do you do that?
So adding the kernel of psi and later image of phi like that.
Standard one, right? So now let me take you to the, yeah. So it basically looks like this. I'm sorry, I had to come to the next page because it ended there. So then, I mean, unfortunately, I don't have a way to show you the earlier page. I have to, no, I have a way. Yeah. I have a way to show you that. Yeah. So it is like this. Okay. So this is what you had started with. This is what you had started with. Then you have these obvious ones. And then you tensor. And your tensoring says that it retains exactness of short exact sequence. I mean, short exact sequences are exact even after tensoring by n. You can complete them into short exact sequences in the obvious way. Then you tensor them out. And then here you have this map. You have these two maps. You want to show that this is exact, right? So that means you want to show the image of this is equal to kernel of this. That's exactly what we are trying to show. So this is obtained by tensoring over R with n. And it has exact rows as well, right? So these are all exact rows, fine. And therefore, you automatically, if you now chase the diagram, so if you want to show to come to this image, then this image will basically see how this diagram is commutative, and you will be able to show that this kernel, if it is kernel here, an element here, then it's going to be exactly equal. See, this is of course contained in this, that's not a problem. You want to show that this, if you take an element in the kernel, then that is coming from the image from here, image of this. So that means you just trace back your exactness and etc. will give you the answer. Okay. So this part again, so please go through it once. And tomorrow's tutorial, although a tutorial sheet will be shared, but tutorial sheet, that sheet will be discussed later on, and your submission will be it will be given some time. But definitely, I don't know if Joydeep is also planning to discuss some problems from there, but definitely these difficulties will be discussed. So the moment you have a question, if you give that question and then if you ask that, it will be definitely discussed. But I can tell you that if you just chase the diagram carefully, you will see why this is happening. Okay, and then 3 implies 1, of course, is obvious, because this is exactly saying that if you take this to be 0 and this to be a map, if the map is injective, means 0, n, m double dash is an exact sequence, and therefore it would follow that tensoring remains keeps it exact, means that means injective maps remain injective after tensoring, so therefore n is flat. Okay, so the main part is basically 2 implies 3, and this is this bit of diagram chasing, what I showed to you. Okay, now, well, this corollary is very, very important. Very, very important, because you will see that when we discuss faithful flatness, this will be exploited again and again. So what it says, although proof, we have already done that. The proof is not difficult at all. That it says that if you look at the kernel, co-kernel, and image, these two things, where they very nicely, they kind of commute with the tensor product, in the sense that they can be taken out. Okay, so if n is a flat R module, provided of course n is flat. So if n is a flat module, and if phi is a morphism of R modules, then the tensor product by with n commutes with the formation of kernel phi, co-kernel phi, and image phi. That is, there are canonical isomorphisms of R modules. So once again, the canonical word should tell you that you just think of the universal property. Okay, and this is sort of a quick discussion on that. But you know what is very interesting is the, let me see. Yeah, here I am. Yeah. So yeah, once again, a quick statement that you have a flatness of, if you have a family of flat modules over any index set I, then if you think of this external direct sum, then this is a flat. Once again, because you know the tensor product actually commutes with direct sum. So with direct sums, it's absolutely fine. Only think of the Cartesian product, you have the restriction. And you have these very important flat modules. This is the free module, and this is the polynomial ring over any number of variables. Okay, and now this is something very, very important. Here it requires some kind of some care. Okay, so n is an R module, n is flat, and if A is a non-zero divisor in R, then this equation Ax equal to 0 for some x in n implies that x is equal to 0. Okay, this is of course something very easy. Why? Because if you take this map from R to R given by this multiplication by this non-zero divisor A, then this map is injective because A is non-zero divisor. And since n is flat, therefore tensoring with that keeps it injective, which means that answering this question, right? Because what is going to be the map? This map is going to be x going to Ax, right? Eventually, isn't it? Because this is n, this is n. These are isomorphic to n. And this R going to AR, this eventually means that you can just take this, the entire thing, it becomes just X going to AX. And therefore, what does it mean to say that it is injective? So if you have AX equal to 0, then definitely you have X is equal to 0. Part 2 is what is interesting. So you look at the statement here, you are assuming that R is a PID. Okay, later on we will see whether how serious this condition is and things like that. So n is flat if and only if any equation Ax equal to 0 for A in R and X in N implies either A is 0 or X is 0. Okay. Now this proof, this is the standard proof, but we will have some non-standard part and some more discussions on that later on. So first of all, this only if proof, only if part you have already proved in one, right? Only if part means that if you, since n is flat, therefore whenever you have Ax equal to 0, then you know if A is not 0 or non-zero divisor, etc. Because A is R is a PID, so non-zero elements means automatically it's definitely a non-zero divisor, and therefore X must be 0. So that part is fine. So the other part is what is interesting. So that means if you have this kind of condition given by this equation, this kind of linear equation, you can say, okay, so then you definitely have flatness of n. Okay. Now how you prove is the following. So first you assume that n is finitely generated. Now, finitely generated module over a principal ideal domain, so it's free. So therefore, you have your, so if part follows, why? Because, I mean, like, because of the free condition, so automatically it's flat, right? Because you just see, this is a very standard example of flat module. But question is, what if it is not finitely generated? Okay, now this is where I will have some issues. Okay. So consider a monomorphism of R modules and an element Z in the tensor product. Okay. So you have taken this injective map, you have tensored this by n, you have this map, and if you want to show that n is flat, then you want to show that this map is injective given that phi is injective. So you take an element in the kernel, isn't it so? Okay, Z, that is summation xi yi, I belonging to I. And now you, when you apply this, then you get this, and it is in the kernel, and therefore this is 0. Now look at this statement. I've also colored it with green, that therefore there exists a submodule n dash of n such that n dash is finitely generated. And looking at the canonical commutative diagram, whatever it is, I'm coming to that. But please remember this question, okay? What ensures this existence of n, this finitely generated submodule? Although I will answer it eventually. So this is the canonical diagram. So let me again keep that page alive. It's here, okay? So you have this, the phi, your phi is from, remember, phi is from m dash to m, and you have tensored it out by n. This is the map you want to show that it is injective, given that phi is injective. From that, you have actually created a finitely generated submodule. Assume that it exists. Okay. There is a finitely generated submodule n dash of n. And then what you are saying, you have a map from here to here, you have a map from here to here, and you have a map from here to here, right? So this is basically the identity, tensoring it with n dash. Okay. Now, first question is, looking at the canonical commutative diagram, once again, I have used the word canonical. So can somebody tell me why, what is so canonical about it? Is this also getting, are we getting it from the universal property somehow?
So if we just take the maps from m prime cross n prime to all of those things, then the corresponding canonical maps will be this, means coming from the universal property.
Right. If you just take the standard inclusion, etc., your bilinearity and everything will be there, and then it would naturally induce a linear map by the universal property. Absolutely. So please take care of this, okay? Because this kind of, this gives you immediate hint that think of universal property. Okay. Okay. Now here is your Z. Z is here, right? You want to show that, and then after, sorry. So you know that after you push it, Z is in the kernel. So after you push it over here, it becomes 0. You want to show that this is 0. You want, in order to show that this map is injective. Okay. Now this element admits a pre-image here. Would you agree? Would you agree? That this element, let me write it here, sorry. So Z is equal to summation xi yi I in I, and this is here. And I'm saying that this admits a pre-image there, and this is in the kernel, don't forget. It admits a pre-image here, that is Z bar. And this Z bar is also in the kernel of phi in identity of n dash. Do you agree to this? That means this actually comes here. And then what would be the argument eventually? Since n dash is finitely generated, you know it's free, and you know that this is flat, therefore this will be injective. Therefore, automatically, you know this will be, since z dash is 0, okay, your z dash will be 0. Why z dash should be 0? Because you know automatically your 0 here, it will be pushed to 0, right? And once you have a 0 here, that means you have a 0 here by exactness and because of flatness of n dash, and therefore this will be automatically 0. That's the argument. Okay. But question is two couple of things. One is, how do you know that there is a lift? And what is this n dash? That is exactly what I have not spelled out here, right? Any guess? If you look at the lemma below, then you will get an answer. But this lemma is the one which demands discussion. So how do you think this n dash should exist is my question.
If we just split out unit tensor terms, summation xi tensor yi, and take those yi's.
Okay. So basically, like to take some finitely generated submodule of n. That's what
you can write 0 as a finitely combination of phi xi tensor yi's, and then take those yi's and take the submodule generated by those yi's. That will.
So let me come to the very precise answer to this. And then
why does Z admit a pre-image?
Sorry.
Why does Z admit a pre-image?
Yeah. See, but the point is, first of all, that what is n dash? What do you mean by saying that Z admits a pre-image? Before that, you have to settle this answer that what is your n dash, isn't it so? I mean, why suddenly for anything on earth it would admit a pre-image? So that is, n dash is the first issue. That what is that n dash? The answer is, why don't you take these yi's and then the submodule generated by them, okay? And then kind of take this. But I'll have a more precise answer than that, a little more precise in the sense, and some discussion is necessary because often there are some casual remarks that it can be proved, but that casual remark is a bit dangerous. Okay, so and see, we are back to this 0 issue, right? So, so it was indeed very important that this 0 has to be settled with care in tensor product. So if m and n are two R modules, consider an equation of this type. So that means, you know, you have this in the m tensor n and the summation I, and with for a finite index, that for a finite set I. Then there exist finitely generated submodules m dash and n dash such that this xi belong to m dash, yi belong to n dash for all I, and such that the equation holds already in m dash tensor n dash in R. Okay. So now question is therefore, so are you thinking of this m dash tensor n dash as a submodule of m tensor n? That is the point. See, your m dash is a submodule of n and n dash is a submodule of n, pretty fine, because you can just take this xi submodule of m and xi and take the submodule generated by them, yi submodule generated by them. And then you do have two submodules, m dash and n dash. So you have an inclusion, m dash contained in m and n dash contained in m. So therefore, you have every right to take the tensor product of these two maps. And that will be a map from m tensor n m dash to, m tensor n to m dash tensor n dash, or rather, and the other way around, m dash tensor n dash to m tensor n. But question is that injective? Understood? Because See, you know definitely that you have a map from M dash tensor N dash to M tensor N. Okay, now can you say that this M is it? So here's the question that can we say that this M dash tensor N dash is a submodule of M tensor N? Now, this is exactly the problem is where the problem lies, because sometimes people just say that we can assume that there is a submodule which contains, but that why is what needs to be settled. Okay. And here, see, all we are saying is that there is a map and we have a pre-image. And once you have a pre-image, because of the exactness over here, then, and because of the exactness, if you can ensure that this element maps to 0, then fine, the exactness says that this element maps, this element is 0, and therefore this must come to 0. So you are fine. Okay. So only thing you have to ensure is that this element, whatever you are calling is a lift, that exists for a suitable N dash, and that suitable N dash, now you know what it is. And this maps to 0. That much is enough actually. Okay. Then because N dash is finitely generated, it is free, it is flat. Therefore, this is exact. Therefore, you have this is 0 because this is mapped to 0, if you have checked that. And this is 0. Therefore, if it maps to 0, if it maps here, then it must be 0. That's the argument. So this is a very, very important question here, that here I have made no mention of this fact that if I take these two submodules M dash and N dash of M and N, when you tensor them out, then that is a submodule of M tensor N. We are not saying, and we are not using either. Okay. And we will now see, this is one instance where you can give a proof of this fact using the construction of the tensor product. But that was my earlier question. No, is it essential? I mean, do we really need the construction? But once again, you know, this construction will give a proof. Okay. But in fact, you can avoid this construction also. So that you will have to wait a little. I mean, like if I think I will have a chance to talk about it later, but I'm not very sure though. But at least I will share it through some tutorial. So how do you handle this using the tensor product construction is very simple. Actually, what you do is, so basically you have to choose a good enough submodule which contains all these xi's and yi's. And you have this M dash contained in M, N dash contained in N. That is obvious because you choose the submodule generated by the xi, submodule generated by the yi's. Okay. And then what you do is all generators of Q that are needed to write this as an R linear combination. Why? Because this is 0, right? Therefore, you know this belongs to Q, right? So this belongs to Q in the sense, in the unquotiented situation, this belongs to Q. So you know Q is generated by all those bilinear relations. So you just take all those which are needed to write this as a finite sum, push them, and then you know this. Let me go to the next page. And then that is what I'm calling Q dash. This Q dash stands for the module of relations needed for the construction of the tensor product. So this is my this thing. So basically, this is nothing but the tensor product of M dash and N dash. So Q dash, how do you take this Q dash? So it is big enough. It takes all the relations which ensures the vanishing of that xi tensor yi. Okay, and therefore you will have this belongs to Q dash. That means in the tensor notation, this is 0 in M dash tensor N dash. That's all you want. Okay, once you have that, and now if you know what your M dash N dash is, then obviously that you know the map. See, let me go to the previous page once again. See, you know the map. You know what the map is. That's not a problem because these are all very nice canonical construction, what we have been saying. There's an inclusion here and the identity map here. So the map here is pretty well known. So therefore, you know what map, which element will actually be mapped into this. Only thing you have to check is that you do have such a module. But we are never trying to say that this is actually sitting inside. That's the main point. You don't need that to say. Okay. Okay. Fair enough. And now I have a few observations. I think I cannot go beyond that. I cannot define the faithful flatness. Oh, I will define the faithful flatness today and then I will stop. And Okay, so the observations are, so one can see that the construction of tensor products has been used to prove the previous lemma. However, one can take a different approach using inductive limits. So I'm not very sure if I would come to this, how the inductive limits and tensor product behave. That's the idea, but I will definitely add it in the tutorial sheet. So is it possible to avoid the above lemma altogether by proving the previous proposition? So we will discuss this later while discussing Tor. Okay, you know, I will be introducing Tor as well. So the following proposition actually gives the answer. If you want to prove, this actually gives you the answer, that if you have an R module N and you don't need PID, and if it is flat, if and this R module N is flat, if and only for every inclusion, you can actually reduce the case to just an ideal A and ring R, where A is an ideal, the induced map is injective. Okay, so this we will prove a little later after I introduce Tor. And this, if you look at this proposition, in fact, you can take it as an easy exercise, that this proposition immediately proves that that this previous proposition, what we have proved just now, that if you have that N is flat, if and only if it satisfies this kind of triviality of that kind of equation, right? Ax equals. Okay, so let me quickly define the faithful flatness. So an R module N is called faithfully flat. Again, you will see the zero is an issue actually, that if it is flat and if M is an R module such that M tensor N is zero, then M must be zero. Okay, so you have previously seen that it could happen that, or rather I have mentioned, and you have to think of an example, and the example is also there if you look at it carefully, that it might happen that after tensor product things vanish, although individually these modules are non-vanishing. Okay, but for faithful flatness, when you are saying that N is faithfully flat, that means this, it can happen, this provided this. So therefore, immediately it ensures that condition 2 immediately says that therefore a faithfully flat module must over a non-zero ring must be non-zero. That much is clear, because otherwise, if this is zero, then everything will be zero, isn't it? So, okay. And the ring homomorphism, just like before, you call that faithfully flat if R dash viewed as an R module is a faithfully flat R module. So this is the definition of faithfully flat. Okay, let me quickly, since the time is up, let me quickly just show you the propositions and I will discuss it in the next class. And anyway, it will be shared with you. So you will have a chance to read these things. So this actually gives a very nice equivalent criteria for faithful flatness, that again, in terms of exact sequence and then in terms of the maximal ideals. Okay. And this proof here, it is written in complete detail. Yeah, so this is basically the last proposition which I wanted to discuss, that here again, you will see that 1 implies 2 is easy. And I mean, like, actually, it's not difficult. So I would say that do go through it once I share my notes. And next class, I'll begin with this. And again, the tutorial session can be used, but tutorial session is only for 1 hour. So you have to sort of be very, very focused when asking questions. Okay. So I think I'll stop here today.